Welcome back to KSET previous year question and solution classes. Today I will discuss 2014 paper from same as it is condensed matter physics or solid state physics or from material science part. Okay. So the question is like this: two-dimensional lattice has the basis vector 2i and I plus 2j. These are the two bases. The basis vector of the reciprocal lattice we have to calculate. If suppose this is our A1 vector 2i and this is our A2 vector I plus 2j and A3 vector they are not given, let us consider that as C k cap. Okay. Next, so unit vector where C is 1, I am taking 1, and if suppose A1, A2, A3 are our lattice vectors, then their corresponding basis, their corresponding reciprocal lattice are B1, B2 and B3. We know that the expression for reciprocal lattice, that is B1 is equal to after 1, okay, 2 pi into after 1 A2 has to come, 1 see 1 after 2 after 3 like that, 2 pi into A2 cross A3 divided by A1 dot A2 cross A3. Next, B2 is equal to 2 pi into, so after 2 3 has to come, so A3 cross A1 divided by A1 dot A2 cross A3, and B3 is equal to 2 pi into A1 cross A2 divided by A1 dot A2 cross A3. So this is the reciprocal lattice expression. So now we are going to calculate a two-dimensional reciprocal lattice vector. I am going to rub this part, this question. See, B1 is equal to 2 pi into, what is A2? See, A2, I rubbed that, right? So sorry, that is okay, A2 I am written here, I plus 2j. So I plus 2j, see, A2 cross A3 can be written as I j k A2, this one, coefficient of I is 1, 2, k 0, and A3, so this is A3 0 0 1, therefore which is equal to I into 2, so this is 2i, A2 cross A3 is 2i. Okay, if I take j 1, so minus j, if I take minus j and the answer is 1, so k, for k it will be 0, therefore A2 cross A3 is 2i cap minus j cap divided by A1 dot A2 cross A3. So now I am going to write A1 dot A2 cross A3 is equal to, so what is the coefficient of A1? 2, so 2, and there is no j term and there is no k term, so that is why it is 0 and it is 0, therefore 2 into 2, 4, so this is 4. Next, and B2 is equal to, okay, 2 pi into A3 cross A1. A3 cross A1 we are going to calculate. So that is, so let's see, A3 cross A1 which is equal to I j k, coefficient of A3 k cap is 1, other are 0, and A1 only 2 is there and other terms are 0. So therefore this gives I terms no 0 and minus j into 0 minus 2, so plus 2, so 2j. Therefore 2j divided by A dot A1 dot A2 cross A3, so that is same 4. So substitute here. Therefore B1 is, if I take 2 as a common, so then it is 4 pi and this 4 cancel, pi into I minus 2j, right, or so there is no 2 here, so j by 2. Next, here B2 is equal to 4 cancel, pi j. Is there any option pi j, pi I minus j by 2? So if we multiply pi inside, it will becomes pi I minus pi j by 2, and this is pi j. So option D is correct. Okay, easy. So this is the question number 52. The question is like this: which one of the following pairs of a crystal structure can have the same packing fraction of 0.74? Okay, so these are the given options: BCC, BCT, and BCC FCC, BCC HCP, and FCC HCP. Body centered cubic lattice or face centered cubic lattice or hexagonal cubic packing fraction, hexagonal cubic structure. Okay, so let's see which one is you will get the packing fraction 0.74. So this is a structure of face centered cubic lattice, and this is hexagonal closely packing, and this is body centered cubic lattice. So in face centered cubic lattice, so there are 8 corners. In the 8 corners there is a lattice, and in each face there is a one lattice, and this lattice is shared with this another surface, another lattice unit. So this is a unit cell, another unit cell, and this lattice point is shared with another unit cell. So here it will come, and here it will come. This is shared with another unit cell, and this is shared with another unit cell below this here. So this is face centered cubic lattice, and this is body centered cubic lattice. Each 8 corner is shared with 8 other unit cells, and this is body centered. This is not sharing with anyone. So this is lattice point, and here hexagonal closely packing structures. Here the 3 corners, the 3 lattice will be inside this hexagonal closely packing. So here, and this lattice is shared with another one more surface, and these 6 lattice points share with other 6 lattice unit cells, and here also these 6 unit cells, these 6 lattice points shares with another 6 unit cells, and this is shared with only one another surface below here. Okay, so now let us calculate packing fraction. So for that I am going to rub this question part. Okay, So atomic packing fraction. Atomic packing fraction means it gives how the lattice are arranged or packed in a crystal, which also gives a density of or hardness of a crystal. If packing fraction is more, so then the crystal bonding is high. It is not possible to break that type of crystal easily. Okay, and also so many properties of these crystals depends on this packing fraction also. So let's see how to calculate the packing fraction. The packing fraction, atomic packing fraction, is equal to number of atoms occupied in a unit cell. So this is unit cell, and into volume of lattice or volume of atoms. So volume of this lattice are atoms divided by volume of a unit cell, volume of this total unit cell. Okay. So what is this unit cell? Unit cell is a repeated arrangement of a group of bases or points in a crystal. So if you take a overall crystal, this type of BCC FCC structure, and in the next cell there will be a same number of lattice points, and there will be the distance of these lattice points are same. So like that atoms are arranged. So let's see, which is equal to number of atoms occupied in a unit cell. So in this unit cell, if suppose this is first I am going to calculate for FCC. This is FCC, body centered cubic structure. Number of atoms occupied in a unit cell, which is equal to number of atoms occupied in a unit cell of FCC, which is equal to, see, this lattice point is shared with all the 8 corners. This 8 corner of the atoms shared with all the 8 another unit cells. So the contribution of the lattice points for this unit cell is 1 by 8 into 8 plus, see, in a phase 1, 2, 3, 4, 5, 6 phases will be there for this cubic structure, and each phase is shared with another, the nearer coefficient, other, for example, this is one cube and this is another cube. If you join this lattice is shared with this surface. So the contribution of this lattice is 2. So that's why it is 1 by 2 into how many surface is there? 6 surface. So total 1, 2, 3s are. So 1 plus 3, which is equal to 4. So therefore number of lattice points or atoms in a unit cell is 4 for FCC. Next, for BCC, let's see for BCC, again these 8 corners share each lattice point with another 8 corners of the lattice. So which is 1 by 8 into 8 plus, and this body center has only one atom, so which is equal to 8 ones are 8. So 1 plus 1, 2. Number of lattice points in a unit cell is 2 for BCC. Next, for HCP, see, in the upper surface you have 1, 2, 3, 4, 5, 6, 7. In the lower surface we have 7, and here we have 3. So 3 plus this 3 does not share any lattice with another unit cell. Okay, so this lattice belongs to only this unit cell, these 3, and see this 1, 2, 3, 4, 5, 6, this upper surface of this 6 lattice points is shared with 6 other unit cells. So which is 1 by 6 into 6 plus this upper surface share with another upper surface, so that is 1 by 2, and this lower surface is also shared with another lower surface, So that is 1 by 2 plus these 6 atoms shared with another 6 atoms. So that is plus 6 by 6. So answer total is 3 plus 6 ones are 6. So 1 plus 1 by 2 plus 1 by 2 plus 1. So 3 plus 3 by 2 plus 3 by 2. So total answer is 3 plus 6 by 2, 2 ones are 2 threes are. So answer is 6. So therefore total 6 number of atoms will be there in a unit cell of HCP, hexagonal closely packing structure. Okay. So now let us calculate the packing fraction, right? See. So which is equal to number of atoms occupied in a unit cell of, first I am going to calculate FCC. For FCC, which is equal to how many? 4 into volume of 4 by 3 pi r cube, volume of an atom. So R, we know that R is equal to root 2 by 4a. So substitute there, root 2 by 4a whole cube divided by volume of a unit cell. So that is a cube. Okay. So if you solve this, you will get the answer is 0.74 for FCC. Okay. Next, if we calculate for HCP, number of atoms is 6 and 4 by 3 pi r cube, r is a by 2. So a by 2 whole cube divided by volume of a unit cell a cube. If you solve this, again we will get 0.74. So answer is FCC and HCP are the same packing fraction. If we calculate for BCC, so then you will get this is approximately 0.64 something, 0.62 or like in that range. So these two are correct option. I think option number C or D. Okay. So this is the question 53. Ionic solids are soft and brittle, hard and brittle, malleable and ductile, and malleable, hard and brittle. So actually ionic solids are hard, because ionic solids, most of the ionic bonds are formed by electrostatic force. So what is ion? Ion means if an atom lose an electron, or if an atom gain an extra electron or extra charge, it behaves as ions. If atom lose one electron, it behaves as a positive ion. If atom gains one electron, it behaves as a negative ion. So ionic bond is made between the force, electrostatic force. It's a charged bond. So that's why it has some attractive force and it has some repulsive force. That's why ionic bonds are strong bonds. So therefore ionic solids are strong. That means strong means hard, but it is also brittle. Why? Because after reaching some temperature, example for ionic bond is NaCl. So this will break the bond after reaching some temperature. So it has also brittle. So what is brittle? Even it is hard, if we give some pressure on this brittle body for this type of solids, it will break. It will break the bonds. So that's why it is hard, but it is brittle. And malleable, ductile. So malleable means even applying a large force pressure on the given surface of a metal, it will not break. It forms into a thin film, but will not break. Example, a clay soil. It is not possible to make a clay soil as a break. It will form like a thin surface. Like example, gold is a very good example for this malleable. Okay, it form into a thin film, but it will not break. And ductile is also same type of malleable, but for a ductile solids it will resist the applied force up to some level. It has more elastic property, but after even applying a load up to some end, fracture end, it will break. So that is ductile. So ionic solids are hard and brittle. So option number B is correct. And question number 54. In case of instability in a cubic crystal, C44 is less than 0, C44 is greater than 0, C11 is greater than C12, or C11 is equal to C12. In case of instability in a cubic crystal, so for a cubic crystal, stability of a cubic crystal says that C44 is greater than 0. Okay. And C11 plus 2C12 is greater than 0, and C11 minus C12 is also greater than 0. But in the given option there is two dissimilars, they are given. C11 is equal to C12. This is not a correct option actually, but C44 is less than 0. So this is the answer, but actually this question is little bit doubt for me also, but in the key answer they are given A, because the condition is not here. C44 is less than 0, C44 is less than 0, this is not correct. So that's why we are taking instability, but this condition is not correct. Okay, maybe here some printing mistake will be there. If it is minus and it is greater than 0, then this is also correct option. Okay, the next class we will discuss. For next question number 56, for copper metal the conduction electron density is 8.45 into 10 to the power of 28 per meter cube. The Fermi wave vector, these are the options given. In these 4 options you have to calculate a Fermi wave vector K. Okay, let's see. So this is the given options, and this is the question given. N. See, we know that for a density of states, energy for a density of states is E is equal to h square divided by 8m 3 by pi whole power 2 by 3 into k power, okay, sorry, n power 2 by 3 for a 3 dimension, and which is equal to h is 6.626 into 10 to the power of minus 34, 8 into mass of the electron 9.1 into 10 to the power of minus 31, 3 by pi into n 3 by pi whole power 2 by 3 into n means 8.45 into 10 to the power of 28 whole power 2 by 3. After solving all this, we will get answer is 7 electron volt. Okay. So now, and also we know the relation EF is equal to h square by 2m into h cross square by 2m into kf square. Therefore, kf square is equal to 2m EF divided by h cross square. Therefore, kf is equal to root of 2m EF divided by h cross square. And after substituting this value, we will get EF means 7 electron volt and mass of the electron 2 and h cross square value. If substituting all this, you will get answer 1.36 into 10 to the power of 10 per meter. And also in the given 4 option, we can easily guess the answer without calculating all this, because the SI unit of wave vector is per meter. Okay, because the formula k is equal to 2 pi by lambda. What is the SI unit for lambda? Meter. So therefore k is equal to 1 by meter. So therefore k is equal to per meter, right? In the given 4 options, per meter is only for B and all other 3 options are in terms of meter. So therefore option number B is correct. Okay. So this is the question number 57. If E is the electric field developed in the presence of a temperature gradient T. So these 2 points is very important here. Electric field is developed due to change in temperature is nothing but Seebeck effect. Don't look any options. If there is an electric potential or electric field is created in the metal due to change in temperature, then that effect is always Seebeck effect. Peltier effect I already explained in the last video. Peltier effect is reverse of the Seebeck effect. Because of change in electric potential due to some chemical change, due to change in electric potential and thermal energy is generated, that is Peltier effect. And due to change in temperature, if electric potential is created or electric energy or electric field is developed, so then that is Seebeck effect. Okay. So option number C is correct. So this is question number 58. A Frankel defect in an ionic crystal is a stoichiometric defect of a cation vacancy, an anion vacancy, a pair of cation and n vacancy, anion vacancy, or a pair of cation interstitial and cation vacancies. See, Schottky defect means if this is the lattice structure, an ion is missing. It moved from this position to somewhere and a lattice point is created. So that is Schottky defect. And Frankel defect means if there is, this is the lattice position and due to this atom will move to this position. This is not actually position for the lattice, but in this position an extra lattice point is created, moved, so developed. So that is a pair of cation or interstitial and cation vacancy is created. So option B is correct. A pair of cation interstitial, if they mention like that, so that is Frankel defect. When a DC voltage V is applied across a superconductor, insulator, superconductor junction. See, if suppose this is superconductor, this is a thin insulator material and this is superconductor. If suppose a DC voltage is applied, so then this is called AC Josephson effect. If there is no potential difference between these two superconductors, so then that is DC Josephson effect. So now if we connect a battery or DC voltage, so then it works as a AC Josephson effect. So when a DC voltage is applied across the superconductor and insulator superconductor junction, Cooper pairs crosses the barrier layer. Yes, option A is 1 is correct. Cooper pairs. That means a pair of electrons will cross from from this end to this end or this end to this end. Option 1 is correct. An oscillating current of kilohertz frequency is produced. Actually, an oscillating current is produced. AC current is produced, but that frequency is omega is equal to 2 EV by H cross. I think 2 EV by H cross, yes, but this is in terms of gigahertz, not in kilohertz. So option 2 is not correct. A photon of energy 2En is emitted or observed. Option 3 is correct. A DC current is produced. No, because you are applying a DC voltage, therefore AC current is produced. So option 4 is not correct. So a very precious value of E by H can be obtained. Option 5 is correct. So 1, 3 and 5 options are correct. Which of the following answers is correct? The question is like that. Okay. So 1, 3 and 5 are correct, and 2 and 4 are wrong statement.